Hi, welcome back to Digital Forensics. We're going to get started again on Chapter 5. We're going to go through Chapter 5 and then cover what we did with Windows, moving on to the registry and other options. So let's go ahead and get started. Here, working with Windows and CLI systems, Windows and CLI systems, a little misleading possibly, but we will be working in the CLI of whatever system we're on since we're doing digital forensics. Now, not all forensics take place within the CLI, but a large portion of what we do will be inside the CLI. So let me see if we can keep this here and click through there. So objectives, we've been through the objectives already and how all of this works, but we're looking at NTFS, Windows, registry, and a bunch of other options and see how these things work together. So file systems, once again, we covered this in class. The OS roadmap to data on the disk, type of file system OS uses determines how data is stored on the disk. We need to access a suspect's computer. Now let's see if I can pull that down like this and make it a little bit bigger. We'll try that. So we need to access a suspect's computer, acquire or inspect data. You should be familiar with both the computer's OS and file systems. And when they talk about file systems, they're talking about NTFS, VFAT, FAT32, EXFAT or XFAT. Of course, you got HP, HPFS, HFS, HSFS plus, second extended file system, fourth edition, etc. I mean, there are a lot. There are a lot of file systems out there. So CMOS, boot sequence, we talk about CMOS, we're talking about the BIOS of the boot of the computer. So nothing new there, and we'll go through the CMOS on how that boots up a system, and everybody's familiar with that. So this is a typical BIOS screen. This is the CMOS setup screen. So as you go through this is what we all see all the time. Now, disk drives are made up of one or more platters coated with magnetic material in the old days, yes. In the new days, not so much. Now, I actually have a couple of images to pop in, so let me pop those images in. There we go. So those images should be on the screen now. You should be able to see the sectors and cylinders, tracks, heads, and the arm of the drive. So over here, if you look, you can see we've got a sector referred to as that little teeny tiny rectangular kind of curved area. And the reason it's curved is because the disk itself is curved. So it's not some, technical situation that came up for some reason they want to divide by pi. It's a circular disk, so the sectors are a little bit curved around the disk. Of course, the computer doesn't realize that. You got the tracks there. The tracks are those lines that go in the circles around the disks, and the platters, of course, are the platters. And cylinders are tracks that are stacked on multiple disks. So when you have multiple disks there, the cylinder is just as you imagine a cylinder like a soda can, whatever it might be, is a cylinder. That's the cylinders that go down through however many platters you have. The heads read on those, and so the heads are above and below that. So moving on. Here is a couple of more examples. It's saying each concentric circle is a track, and yes, it is as it goes around. Each wedge-shaped area is a sector. Yes, it is. Those little wedges right there are sectors, and each combination of tracks forms a cylinder, which is stacked on another platter, and that is that three-dimensional view that we get. Now, this used to be really significant. It still is significant because we use mechanical drives on a regular basis today. Mechanical drives really have no indication that they're going away permanently at this point because mechanical drives can be rewritten, for decades. So some mechanical drives still exist and they're over 10 years old. So they could keep being rewritten and rewritten. Now the NVMe drives and SSDs, they have a limitation to their IOs. So as many input-output operations that you run into that drive, it will terminate over a period of time. It will wear out. So that's the reason that mechanical drives are sticking around. However, this book doesn't really cover how those new disks work. So when we talk about things like zone bit recording or track density or areal density or head and cylinder skew, those things are usually what we reserve to mechanical drives, reserved for mechanical drives, not in the NVMe or the SSD type arrangements. All of those are in your book, but we'll cover what those are really quickly. Okay, with zone bit recording there, it shows that you're actually recording the bits to a particular zone on your mechanical drive. Again, we're discussing mechanical drives, which do have a tendency to be ancient, but just remember mechanical drives will be used into the distant future as far as we understand. So zone bit recording over here is a method of physically optimizing the utilization of a hard drive by placing more sectors in the outer tracks than in the inner tracks. This technique is also known as zone bit recording, etc. So a bunch of options there. Moving on. Track density is exactly kind of what it sounds like. It's the number of tracks per unit length measured in a direction perpendicular to the direction in which the tracks are read. So how many tracks can you fit going around in that direction on a mechanical drive again? And these are mechanical drive terms. Now, areal density is, again, what it sounds like. Think about area density, and that is how much you can compact into whatever area of the disk that we're discussing. So if you're moving a lot of things into a certain area of the disk, it's like gigabytes per inch or whatever it might be. Let's see, what is it? Areal density is a measurement of the amount of data that can be stored on a given unit of physical space on storage media. It is most frequently measured in gigabytes per square inch and used to describe hard disk drive capacity. So areal density. Next, the head and cylinder skew is the offset distance from the start of the last track of the previous cylinder so that the head has time to seek from cylinder to cylinder and be at the start of the first track of the new cylinder. So there you go. That's a mechanical drive. That's how mechanical drives work. Unless you're going into mechanical drive repair, all of that probably makes no difference to you. In a forensics environment, you're not really going to be using that unless you're doing platter recovery, and that's physical hard drive recovery in cases of damaged drives, attempted destruction, or if you're looking at something like fire damage, etc. So one of the things that just we have to cover. Now, moving on, solid state storage devices. All flash memory devices have a feature called wear leveling, and that's an internal firmware feature used in solid state drives that ensures even wear of reads and writes for all memory cells. When dealing with solid state devices, making a full forensic copy as soon as possible is crucial in case you need to recover data from the unallocated disk space. Now, wear leveling on here does mean that a solid state drive will overwrite information that has been deleted much more readily than a mechanical drive will. That is why you have to copy the drive as soon as possible when you get a solid state disk. So if you get an NVMe drive or a SSD, get that thing, image it as quickly as possible, because just booting it up, if somebody boots it inside of Windows, Windows is going to write a stamp on that, and that could actually overwrite some information. So be careful with that whenever you're getting evidence. Of course, we discussed evidence collection and that you should image the evidence as quickly as possible. Okay, Microsoft file structures. In Microsoft file structures, sectors are grouped to form clusters, storage allocation units of one or more sectors. Clusters range from 512 bytes, and remember 512 bytes is as small as we can get on that little, on any kind of transfer that we do, because that the 512 bytes up to 32K, whatever it might be, but at 512 bytes, each bit, meaning if you have 8 bits, you have a byte. And so that would be every letter on the drive would be simply, a single letter would be 8 bits. So you would have those 8 would be just like the letter A. So not very useful in recovery, whereas you get 512 bytes and you can actually have words in there and you can do a full recovery. So 512 bytes, the smallest sector size that we can use. Combined sectors minimize overhead of writing or reading files to a disk. Yes, Microsoft does that clustering, so you can still do the 512 while you still can go through and use larger allocation sizes for improved drive performance. Okay, a partition is a logical drive, and this is where we get to a little misunderstanding between physical partitions and extended partitions, virtual machines, and logical drives versus physical drives. All right, so a partition is like a logical drive. It's really a partition, and what that is the disk has been divided up into a maximum of 4 partitions. Now that's in the old MS-DOS file system. If you have it formatted in MS-DOS, it's 4, which 3 of those can be primary, and then the 4th one you would use as an extended in order to give you another 4 on that disk. So you have a maximum of 0 through 7. One of those being extended, which can't be used. So if you have an extended partition, you can't write information to it. It's just an offset. That allows you to store another 4 partitions, which gives you 7 total. Now, Windows OSs can have 3 primary partitions followed by an extended partition that can contain 1 or more logical drives. Remember, you can make 4 partitions, but if you make 4 partitions, you cannot extend it. You will actually have to delete a partition in order to extend the information. So partition gap used space between partitions, and that's going to be whatever is there. Usually it's not much space at all. Now we looked at this with the MBR. We dumped an MBR, and then we looked at hex dump WX, which is the Windows hex editor. That's just a Python WX. And then we have ghex and hex edit, a bunch of very useful tools, and you can actually look into the boot sector. Well, it's actually the boot table, I guess. The master boot record, MBR, on your system. And so when you look through those kind of things, you can look at your disk and then find the partitions and some names inside of them. You can also see how you might want to put a virus in the master boot record and any kind of spare space that you might have. As we looked at it, partition table and a hexadecimal editor, we went through this and we did look at this in class. We will be doing some labs later on, but those labs are going to start dealing with Windows registry and how do we recover information from the Windows registry. So file allocation table right there, the file structured database that Microsoft originally designed for floppy disks. That's FAT. FAT database is typically written to a disk's outermost track and contains file names, directory names, date and time stamps, and the starting cluster number and file attributes. 3 current FAT versions. We have FAT16, FAT32, and exFAT. And exFAT is used for all kinds of different things, but I like using exFAT because if I format exFAT in Mac. You get a Mac and you format an exFAT. You can use it in Windows. You can use it in Linux. So you can use it in all the devices. Or you can get Linux. You can change it to a GPT, format an exFAT, and then you can use it in all your devices. Especially between Linux and Windows. Mac is sometimes picky, so watch out for that. All right, over here we've just got a table discussing the sectors and bytes per cluster. If you want to go ahead and look at that and how that works, that's great. It's not something that I would ever use in the field, but there you go. It's something that is good to know. So over here, Microsoft OSs allocate disk space for files or clusters, results in drive slack, unused space in a cluster between the end of an active file's content and the end of a cluster. We looked at that in the board saying, okay, we've got a cluster here. We'll say it's a 32K cluster. If you have a 32K cluster and you're only using this first portion of it, then all of this is just free space. That is not used. So the very first portion is used, and this is free space, and the next cluster is shifted on over. The next cluster is what's getting used. So be aware that you will have drive slack in there, and when we talk about recovering slack space, we are looking at all of that space of unused clusters that was on the drive. So drive slack includes RAM slack and file slack. So an unintentional side effect of FAT16 allowing large clusters was that it reduced fragmentation as cluster size increased. All right, so we look over here, examining FAT disks. We got the end of file there. We got the RAM slack, 120 bytes, and then end of 10th sector, 5,120 bytes. That's where we've got all of that slack there because the file was so small, it did not use up the entire cluster. Now, when you run out of room for an allocated cluster, OS allocates another cluster for your file. It does not fill in that space at the end unless you're using the clustering that Microsoft has on certain systems where each one's set in 512 byte increments, and then those 512 bytes are combined into a larger cluster, and then it allows subdivision of those clusters. So when you run out of room for an allocated cluster, OS allocates another cluster for your file. As the files grow and require more disk space, assigned clusters are chained together. The chain can be broken or fragmented. When the OS stores data in the FAT file system, it assigns a starting cluster position to a file, and data for the file is written to the first sector of the first assigned cluster. So we look through here, example of Word 2003 document. We have a whole bunch of clusters. You'll see that we got 478, 479, 480, 1, 2, and 3. And over there, we got those 6 clusters. They're all contiguous, and that's really nice to see. What you'll find in other systems is that those will not be contiguous and that will run out. So when a first assigned cluster is filled and runs out of room, BAT assigns the next available cluster to the file. If the next available cluster isn't contiguous to the current cluster, the file becomes fragmented because it takes it from the first part of the disk and then allocates it somewhere else. If you're using a mechanical drive, of course, you'll go to some other track and it puts the information over there. That's fragmentation. And so that's all of the Microsoft section right now as far as the FAT disks. The next section, we get into deleting FAT files and looking at NTFS. So let's just go ahead and talk about deleting FAT files. And next section, we'll get into NTFS and we'll continue file systems in the next video. So in Microsoft OSs, when a file is deleted, the directory entry is marked as the deleted file with the hex E5 character replacing the first letter of the file name. The FAT chain for that file is set to 0. Data in the file remains on the disk drive. It is just removing the reference to the file. The area of the disk where the deleted file resides becomes unallocated disk space. Unallocated as in the map no longer has that area allocated. The data are still there. Available to receive new data from newly created files or other files needing more space. That's how that works. Okay, that's all for the FAT file system. Next we come back, we'll start with click NTFS, and we'll look at NTFS disks. I hope that this helps, and I hope that the shorter presentation here will be advantageous as you go through the chapter. Stay well. Look forward to talking to you again soon.